Okay guys, so this is isomerism, reforming and cracking, and I'm going to start off by talking about cracking. So basically what I've drawn up on the board here is the official government statistics, and definitely not something I've just made up, of demand for the chain length against the actual chain length. And as you can quite clearly see, as the chain length gets bigger, the demand for that chain of hydrocarbon gets smaller. So the shorter chains, the 1 carbon and the 2 carbon chains, there's a lot more demand for them. And obviously because of that, people will pay a lot more money for it. So what we're going to talk about today is cracking, which is a way to change a long chain into a short chain. So let's look at why short chains have got such a high demand. Okay, to talk about this, we need to think about what happens when a fuel burns. Not many people know this, but when you burn petrol, it's not actually the liquid petrol you burn. What you're burning or combusting is the fumes, the vapours on top of the liquid. Okay, so in order for a fuel to actually work, it has to be able to change into a gas. If it can't change into a gas and it stays as a liquid, it won't be a very good fuel. The easier it changes into a gas, the better the fuel is. So let's have a look at some different length carbon chains. Let's have a 1 carbon chain, a 2 carbon chain, and a 3 carbon chain. And I'm going to have 2 molecules of each. Okay, my 1 carbon chains have only got 1 carbon in them. So I've only got 1 set of van der Waals forces. My 2 carbon chains have got 2 sets, and my 3 carbon chains have got 3 sets. So as the chain length gets longer, as it increases, the amount of van der Waals forces between my molecules gets stronger. And that means it's harder to break them up and change them into a gas. So short chains, like 1 carbon, are incredibly easy to change into a gas because they don't have strong forces holding them together. Which is why methane gas, which comes out your gas taps at college, is a gas. And the longer it gets, the stronger the forces they have, so the more likely it is to stay as a liquid. If you look at the video of fractional distillation, we talk about this there as well. So basically, the shorter the chain, the easier it is to change into a gas, and the better the fuel it will be. And since one of the main things we use alkanes for is fuels, that's why there's more demand for shorter chains. We've got a problem. If we take crude oil out of the ground, most of it isn't in short chains. It's in either medium or long chains. So we need a way of breaking these long chains into short chains. And that's what cracking is. It's the breaking down of long chains into short ones. And it basically works like this. Let's say I've got a 6 carbon chain with my hydrogens on. I'm not going to add the hydrogens on the end because I'm lazy, but there should be hydrogens on the end here, and in an exam you need to add the hydrogens on. Essentially, what we do when we crack something is, you can think about getting a pair of scissors and snipping it in half. So we just literally break a long chain into smaller ones, and we can snip it into 2 chains, into 3, into as many chains as we want, provided we've got enough carbons. Usually in an exam though, they'll only break 1 chain into 2. So that's the example I'm going to go through. And we can break any bond we want. Let's say for example, I break this bond here. Okay. What happens is when we break the bond, you can think of the bond as swinging around. So rather than being joined from this carbon to this carbon, it joins back round to this carbon. So I now have a double bonded molecule, and I've got my 2 hydrogens here, and I've got 3 hydrogens here, but that's too many because carbon can only make 4 bonds, so I have to get rid of 1. So I've got 1 hydrogen in the bank, and I've got my 4 carbon chain here, and I've got my hydrogens, and this carbon now only has 3 bonds. It needs an extra bond, but oh look, we've got a hydrogen in the bank, because remember it got lost from this one, so we just add it onto this carbon, and we're left with a shorter alkane and an alkene. So if I started off with a molecule with no double bonds and I cracked it, I'd end up with a set of molecules all in all, and you'll have one double bond amongst them. If I started off with a molecule with 7 double bonds and I cracked it, I'd end up with a set of molecules with a total of 8 double bonds. So you always increase the double bonds by 1. And we can test this by adding bromine water. If you add bromine water to a double bond, what happens is this. The double bond breaks, so bromine water is just Br2, like that, and this is a nice orange colour. If I add it, the double bond breaks, that bond breaks, and 1 bromine goes to each of these carbons. So I'm essentially getting rid of my bromine. So this nice orange colour, nice deep orange, goes colourless. So you can tell whether you've got a double bond by adding bromine water, and it goes from orange to colourless. Okay, we've also got isomerism and reforming. Reforming is basically where we take a straight chain and we make it into a cyclic chain, so a circle, although it won't be circular. For example, one, two, three, four, five, six. So this is hexane. If I reform it, what will happen is I essentially join up my carbon ends together. Now, carbon can make 4 bonds. At the moment, it's already got 4 bonds. So before this carbon can join up to this carbon, each of these needs to lose a hydrogen. So I'm going to lose a hydrogen from the end here. I'm going to lose a hydrogen from the end here. And that just goes off as hydrogen gas. And then, since each of these carbons now only have 3 bonds each, this carbon can join to that to make a nice circle. And I say circle, it's not a circle, this will be a hexagon, but it's roughly circular. And these will each have 2 hydrogens each to make a total of 4 bonds. Okay. The most common ring is a 6-membered ring. You could get different amounts of carbons, like 5 or even 4 carbons in your ring, but usually you'll get 6. Okay? And the reason we do this is, again, to make it a better fuel. So if you have a straight chain and another straight chain, they can pack really close together. So because they're really close, their van der Waals forces are going to be very strong. And that means it's going to be a lot harder to change it into a gas, because the van der Waals forces are keeping them together. If I make them cyclic into a circle, there's less points of contact. They can't pack as closer together, so less van der Waals forces, easier to change into a gas, they combust better or easier. Okay? So the reason we do reforming is to reduce the van der Waals forces, stop them packing as closely, to make them a better fuel, to make them combust easier. And don't forget, hydrogen gas is always given off. Whenever I'm marking mock exam papers, people always forget the hydrogen gas. Try adding up the hydrogens here, adding up the hydrogens here, and you always have 2 left over. So don't forget that. And finally, we've got isomerism. Isomerism it's done for the same reason as reforming, but you do it by a different way. So here we start with a straight chain, let's say a 5-carbon chain, so pentane, and we take our straight chain and we make it into a branched chain. So we basically make this into a different structural isomer. We switch the carbons around. So an example of how we could do that is by sticking a carbon there. Okay, and now no hydrogen gas given off here, it's all just one molecule to one molecule. But now, rather than having a straight chain, we have a branch chain. So again, straight chains can pack really close together, a lot of strong van der Waals forces because they're so close to each other. Doesn't change into a gas, it's a bad fuel. If I make it branched, now they branch like that, they can't pack as close together. There's less points of contact. So the van der Waals forces are weaker, it'll change into a gas easier, and it will burn better or more efficiently. Okay? So reforming and isomerism are done for the same reason, they just go about it a different way. and cracking is just to make the change shorter. And if you get asked a question about processing crude oil, it'll probably be like an 8 or 9 or even like 10 mark question. You can talk about all 3 of these things, because these are all 3 ways we can process crude oil. There's also fractional distillation, that's a way of processing crude oil, and that's in a different video clip, so you might want to watch that after this if you haven't already. And that is cracking, isomerism and reforming.